let us understood once again by drawing a figure on this tabletop what the questions which are asked, because until and otherwise you haven't understood the data of the problem, it is very difficult to give the solution of that. What the statement is that a one circular section of wood is there with us. Please, on the tabletop, on this tabletop, please. Yes, I have to cut it down one portion. If this is B, this is D, we have to cut by this ratio so that we can achieve maximum moment of resistance. Diameter is given to us D, diameter of circular log of wood. Thing is stated on this tabletop that D by B ratio, we have to cut this section by D by B ratio of 1.414. Now, given data, diameter of log D, small d, let A, B, C, D be the strongest rectangular section which can cut off the cylindrical log. Let B is the width of the strongest section, and H, instead of D, capital D, we are defining as it is H is the depth of the strongest section. Now, section modulus of the rectangular section is given by BH square by 6. H is the one major dimension of the rectangular section. Now, in this equation, the B and H both are the variable. B and H are both are the variable, and the known quantity is the diameter of the circular log of wood. So, we have to relate these two variables with the one given data, that is a small d, and that is given by the rule of Pythagoras, that is B square plus H square is equal to D square. Hence, we achieve H square is equal to D square minus B square, and if we are replacing the term over here, Z is equal to B by 6 bracket D square minus H square, its whole square. Because directly H square is given to us, so we do not have to carry out the square over here. Please be careful, because H square directly value we have to replace over here. So, we achieve Z is equal to 1 by 6 bracket B D square minus B cube. Number 2 number equation. This is my first number equation, this is 2 number equations. Now, in this equation, D is constant, small d, diameter of log of wood. Hence, only variable is B from this equation. Now, for the beam to be strongest, the section modulus could be the maximum. Section modulus should be the maximum value right now. So, here in this data, or we achieve an equation in such a way that only one variable we will achieve in terms of B. So, if we are referring the second equation, Z is equal to 1 by 6 BD square minus B cube. So, only one variable parameter is there over here. So, maximum value of Z, dZ by dB is equal to 0. So, d by dB of, we are replacing, which is equated to 0 by the value of Z over here. So, here the term d is constant. So, d square, d by dB of B is one value, minus 3b square by 6 is equal to 0, and VHU, we get a relation between D and B by terms of D square is equal to 3B square, number 3. But from the triangle using the Pythagoras, we know the relationship D square is equal to B square plus H square, and if we are replacing the value over here D square, so we got it, B square plus H square is equal to 3B square, or VHU relation between H and B, H square is equal to 2B square, VHU S is equal to under root 2B. So VHU H by B ratio is equal to under root 2, because our intention is to establish the relation between the one of the dimensions of the rectangle and the other dimensions of the rectangle, and we achieve it as H by B ratio is equal to root 2 is equal to 1.414. This is number 4th equation. Now the another component part, means the part which is proved over here, that is the maximum moment of resistance which can be achieved by a ratio of H by B is equal to 1.414, and if we cut with this relation between H and B from the circular section, we can achieve the maximum strength of section, we can achieve the maximum moment of resistance in this particular given data. Now the numerical data where D is, which is given to us as 300 mm diameter of log of wood, and we know the relation between D and B, that is 3B square is equal to D square is equal to 300 square is 90,000, and we HU B is equal to 173.2 mm and H is equal to root 2B is equal to 249.95 mm. So if the diameter of the circular log of wood is of 30 centimeter, 300 mm, I have to cut it down a rectangular portion in such a way that the B is equal to 173.2 and D is equal to H is equal to 249.95 mm to achieve maximum moment of resistance. Let us switch over to the today's last problem. An overhanging beam subjected to the 3.2 kN per meter load UDL throughout as shown in the figure. Figure shows very much clearly an overhanging beam. The distance between the two supports is of 3 meter and 1.5 meter is the overhang projections beyond the support B, and this beam is subjected to the UDL is of 3.2 kN per meter. For the cross section of the channel section, yes, its channel section is given to us over here. T is equal to 12 mm, that is the thickness is 12 mm, throughout the thickness is of 12 mm, and B is equal to 300 mm, this dimension is 300 mm, H is equal to 80. Means the cross sectional dimensional properties which has been known to you in terms of the channel section. Determine the maximum compressive and tensile stresses in the beam. I have to determine maximum compressive and tensile stresses in this particular beam. Now, to determine this maximum compressive and tensile stresses in this beam, the step number 1 is to find out. I have to plot the shear force and the bending moment diagram. Okay, now let us do it. I assume at this level that you can do by yourself, and we achieve this is the shear force diagram and this is the bending moment diagram. From the bending moment diagram, it is very much clear that maximum positive bending moment is of 2.025 kN into meter, while the maximum negative bending moment diagram is of 3.6 kN into meter. What is the need to plot shear force diagram? Because we are not using this anywhere in this particular problem, but the need is to achieve the maximum bending moment, because m over I is equal to f over y. M over I is equal to f over y. So m by z is equal to f. I know the maximum bending moment, and to achieve the maximum bending moment, the location is where the shear force is 0. So now let us go ahead in this problem. We want to find out the neutral axis of the section, and hence to find out the neutral axis I have to use the concept of CG. I have divided the given section into 3 parts, A1, A2, A3, and I found out the CG as 18.48 mm, while the C2, that is H minus C1, is 61.52 mm. Now, moment of inertia of the section is given by the relationship, that is basic fundamental using the parallel axis theorem. I wish you can do at this level by solution of the so many numericals, and we found out the value as if of 2.469 into 10 raised to 6 millimeter raised to 4. So we can find out the section modulus. Here it is S1, you can call as a Z1 and Z2, because C1 and C2 two are different thing. Our intention is to find out the top compressive and the bottom tensile stresses. So these are the two different answers of the section modulus. We know the maximum positive moment, and we achieve the stress, tensile stress sigma t is equal to m by z. We obtain the answer as 50.5 megapascal, while compressive stress is of 15.2 megapascal of the negative side. So now at the section where the maximum negative moment comes, we can achieve by m by s1 and m by s2. We have these answers. Now hence sigma t maximum occurs at the section of maximum positive moment, and this is the answer, while the compressive stress occurs at the section of maximum negative moment, and this is the answer. Summary of this particular session: from this throughout the chapter, we studied the concept of bending stress and section modulus. We studied the concept of bending equation and the moment of resistance. We draw the bending stress distribution diagram, and we have calculated the symmetrical and unsymmetrical sections, the bending stress value. So from the today's session, we solved the sum of the numericals, and today we have completed the chapter of bending stresses. In the next time series, we are starting for the shearing stress in the beams. Till now, thank you.